Hey, what's up everybody? In this video, I want to spend some more time discussing electrophilic aromatic substitutions. Now, specifically today, I'm going to be talking about halogenation, right? So, when talking about halogenation in the context of EAS, um, there's essentially two different flavors of halogenation, right? We're going to have bromination and chlorination. So, in bromination, you're going to have some sort of aromatic compound. In this case, I chose the prototypical aromatic species, benzene. Now, benzene is going to react with Br2, and it's going to do that in the presence of an iron 3 bromide catalyst. Now, assuming you do this reaction correctly, what you should generate is bromobenzene, HBr, and you should regenerate that iron 3 bromide catalyst, right? Because it's a catalyst, it's not consumed in the process of a reaction, and therefore should be regenerated by the end of a reaction. All right, so this is bromination. Chlorination follows a very similar logic. Again, we have benzene, and you're going to react that benzene with some Cl2. And you're going to do this in the presence of an iron 3 chloride catalyst. Now again, assuming you do this reaction correctly, what you should generate is chlorobenzene, HCl, and you should regenerate that iron 3 chloride catalyst. All right, so regardless of whether or not you're talking about bromination or chlorination, the mechanism is essentially going to be the same. So for the sake of this discussion, I decided to put up the mechanism for the bromination reaction. But again, whether you're talking about bromination or chlorination, the mechanism's essentially going to be the same. It's just, wherever you see BRs down here, just replace those BRs with CLs. All right? So before we dive into this mechanism, I want to remind you the basic steps behind really any electrophilic aromatic substitution. And I talked about these basic steps in my intro to EAS video. But basically, when you're doing an electrophilic aromatic substitution, there are two steps. In the first step, you have some aromatic compound, and it's going to react with an electrophile. Right? And in the process of reacting with that electrophile, you're going to generate an rhenium ion. Right? And the rhenium ion is not aromatic. Right? So that's the first step. Aromatic compound reacts with electrophile to generate something that is no longer aromatic. Second step of EAS reactions, there's going to be a deprotonation, and that's going to restore aromaticity. All right? So in step one, when you have your aromatic compound, it reacts with an electrophile. In order for that to occur, there must be, an aromatic compound, and there must also be an electrophile. So, when talking about bromination, the first thing we need to actually do is to generate an electrophile that is suitable for EAS. All right, so that's the first step we have over here. So, basically, we're going to have Br2 react with our iron 3 bromide catalyst. Now this Br2 is going to essentially act as a Lewis base, an electron pair donor, and this iron 3 bromide is going to act as a Lewis acid, an electron pair acceptor. All right, so in your Br2, pick one of your bromines, doesn't really matter. In this case, I chose this one. Now this bromine has some lone pairs on it. Again, doesn't really matter which lone pair you pick, just pick one of those lone pairs. One of those lone pairs will then flow into the iron atom here, and you will get a coordinate covalent bond between this iron and this bromine. All right, so between these two atoms here, you're going to get a coordinate covalent bond. It's basically just a special type of covalent bond in which both electrons within the bond initially came from the same atom. All right, so you have a Lewis base reacting with a Lewis acid. you're going to get a coordinate covalent bond formed between these two atoms here. And the coordinate covalent bond is shown here in the Lewis acid-base complex, also known as a Lewis adduct. All right? So this portion right here, that was essentially our iron 3 bromide catalyst, and down here was our Br2, and this is the coordinate covalent bond that was formed. Again, a coordinate covalent bond, just a special type of covalent bond in which both electrons in this bond initially came from the same atom. All right, so we have this Lewis acid-base complex, and notice that the iron atom has a formal negative charge associated with it, and this bromine has a formal positive charge associated with it. Now, the reason we form a Lewis acid-base complex is because we want to polarize this bond right here between the Br2. We want to polarize it. We want to weaken it. We want this Br to be basically our electrophile. We're trying to weaken this bond so that we can generate a suitable electrophile for electrophilic aromatic substitution. All right, so the first step, Lewis base reacts with Lewis acid to give us Lewis adduct. This Lewis adduct has a coordinate covalent bond in it, and it also has this polarized, this weakened bond in this. And this polarized bond allows us to generate an electrophile that's suitable for EAS. All right, so now benzene's going to walk by, and it's going to use 2 of its pi electrons, and it's going to reach out and grab this terminal bromine, right? That bromine that has a polarized or weakened bond here. All right, so benzene's going to come by and grab this bromine, and that polarized bond here, given the fact that it's weakened, these electrons are going to flow back up onto the bromine atom. All right, so you're breaking this bond right here, and so this is what we'll have left over with regards to our Lewis adduct. Notice that this bromine atom, where it's positively charged over here, is no longer positively charged, right? That's because these electrons are flowing back onto this atom. And notice that we had our aromatic benzene, but when it reaches out and grabs this bromine, it's no longer aromatic, right? So this is our rhenium ion here. All right, so in this step, we generated an electrophile, and benzene comes by and grabs that electrophile to give us our non-aromatic rhenium ion. So now we have to undergo a deprotonation step to restore aromaticity to this species here. And so here's how we're going to do this. Remember our Lewis acid-base complex? So down here we have the remnants of that complex, and basically you can choose any bond here. You can choose any iron-bromine bond, doesn't really matter. I chose this one. The electrons in this iron-bromine bond, those electrons are going to reach out and grab the hydrogen connected to the carbon that's connected to our electrophile, our bromine atom, right? So these electrons here are going to reach out and remove this hydrogen. Now the electrons in this hydrogen-carbon bond, these electrons are going to flow back into the ring system, and that's going to regenerate aromaticity, right? So going from here to here, we've regenerated aromaticity, and in fact, we've generated bromobenzene. So now, also notice that this bromine atom, because this bromine atom is forming a bond with this hydrogen, we're also going to form HBr. All right? And notice we've also regenerated our catalyst, this FeBr3. So here we have FeBr4 minus, but this bond here is going to be broken, so that gives us FeBr3. So we've regenerated our catalyst. All right, so just to quickly recap what we talked about today. We talked about electrophilic aromatic substitutions. Specifically, we talked about halogenation and how halogenation basically comes in two different flavors. Those two flavors being bromination and chlorination. With regards to the mechanism for bromination and chlorination is essentially the same. In the first step, you're going to have a Lewis base react with a Lewis acid to form a Lewis adduct or Lewis acid-base complex. And the reason we form this is so that we can generate an electrophile that is suitable for electrophilic aromatic substitution. And the reason that this generates a suitable electrophile is because this bond here is polarized, it's weakened, it's primed to be broken. All right? So we have this electrophile here, and benzene's going to walk by and see that electrophile. It's going to reach out and grab that electrophile, and that's going to break aromaticity in our benzene, giving us this bromo-arenium ion, right? Now, to restore aromaticity in this species, we're going to have a deprotonation event, right? So the remnants of that Lewis acid-base complex is actually going to facilitate this deprotonation event, right? So what are these FeBr bonds here? The electrons in that bond are going to come by, pluck off this hydrogen, and then the electrons in this hydrogen-carbon bond are going to flow back into the ring, thus restoring our aromatic ring system. All right, so that's it for electrophilic aromatic substitutions with regards to halogenation. You might be wondering, why isn't iodine and fluorine on here? And the reason for that is that, yes, you can get iodines and fluorines onto aromatic rings, but typically the method outlined here, typically it doesn't really work so well when trying to do this with iodines and fluorines. Typically you have to use other means to get iodines and fluorines onto aromatic ring systems. All right, so that's it for halogenation and how it relates to electrophilic aromatic substitutions. But stay tuned because I think in the next video I will be discussing nitration. So with that being said, let me know if you have any questions. Just leave them in the comments section below, and take care, everybody. Thanks for watching.